Welcome to all in the new lecture that is on the solution of recurrence relation by the generating functions. So here till now up to the lectures we discussed about the solution of the recurrence relation by iteration method, characteristic root method. Now in this lecture we discuss about the solution of recurrence relation using the generating functions. And what is the generating function? We studied about it in the last lecture, that what is the generating function. So here this is our the generating function. You know that g0 plus g1x plus g2x square g3x3. So this type of series, this is our the uh, in the generating function we have the this type of series, and in the another way we can say that in the summation form we can write it summation of k is equal to 0 to infinity gk x raised to the power k. So this is the series, that is the generating function. So here we have some generating functions. Here it is a table in which we have the terms is given here in this table, and these are the generating function of these sequences. Actually this is the term, suppose 1, so 1 it means that the summation of 1, right? It is only gk, it is only that gk value, that is 1. If it is 1, it means that all terms of this sequence is 1. And you know that the generating function of the, if we have the series is 1 1 1 1, so that generating function is 1 upon 1 minus x. Similarly, this is only the gk, means these all terms we take with the summation, so that generating function is this. So if we have the gk is k plus 1, means that is summation k is equal to 0 to infinity k plus 1 x raised to the power k. It means that the generating function is 1 upon 1 minus x whole square. Similarly, if we have the gk is k here, so that generating function will be x upon 1 minus x whole square. And if our function term is k plus 1, that generating function will be 2x upon 1 minus x whole cube. And if we have the generating terms are k plus 1 k plus 2, so that generating function will be 2 upon 1 minus x whole cube. If our genetic term is a raised to the power k, so that is genetic function is 1 upon 1 minus ax. You know this. So we use these terms, these genetic functions of these terms in the solution of the recurrence relation. Clear? So let's take some examples to solve the recurrence relation by the generating function here. So if our example is that we take that generating function an plus 2 minus 3an plus 1 plus 2an is equal to 0, and the initial conditions are given that a0 is equal to 2 and a1 is equal to 3. So now you will see that how can we solve this recurrence relation by the generating function. So here first of all we have to multiply this recurrence relation, this equation, with x raised to the power n. Why we multiply this with x raised to the power n? Because we use here the generating function to solve this recurrence relation, and our generating function is the uh, z0, like that, z0 plus g1 x g2 x square. So we have the x raised to the power k terms, right? So here if we have x raised to, we have to multiply this equation by first x raised to the power n, and sum it means that the summation from 0 to infinity. So this is an important thing and you have to understand this. Here we take that 0 to infinity. So how we take here the summation is 0 to infinity? Because you can see here in this recurrence relation we have the uh, we have the order is less, or term is a n, right? This is n plus 2 n plus 1 and n. So lessing term is a n. So when we put here n is equal to 0, so we get the initial value, and that is given the initial condition is a0. So we have to put here n is equal to 0 to infinity. We have the two types of recurrence relation. We can write this, right? You know that in one is in terms of plus and second one is in terms of minus, means n minus 2 and minus 1 and like that. So whichever you have the lesser term, so here our subscript is less is n here, so we have to the summation take from 0 to infinity, because our initial condition, when we put n equal to 0, so we get our the first initial condition, initial that is a0, right? So here we take the summation 0 to infinity. It's clear? Okay, so let's take the next step. So here we multiply this x raised to the power n the whole terms, and the summation we take n is equal to 0 to infinity. So we have this type of expression. Now after that we expand these. So when we expand these, so put here n is equal to 0, 1, 2 like that up to infinity. Similarly here, so when we put here n equal to 0, so we get here a2 and x raised to the power 0, so it become 1. Second term is uh, for the first term the second value is n, put n equal to 1, so it become a3x. When we put n equal to 2, so it become a4x square and so on. Similarly in the second term we have minus 3, and when we put here n is equal to 0, so we get a1 plus a2 x raised to the x plus a3x square and so on. And the third term plus 2, when you put here n is equal to 0, 1, 2, so it become a0 plus a1x plus a2x x square and so on. Now we know that what is our generating function. Our generating function, we can express our generating function gx is a0 plus in terms of a0 plus a1x plus a2x square is like that, right? So now we have to put in this term of g or the this series. So we manipulate above equations in terms of the g. So each term, actually each term of this recurrence term we have to express in terms of g, in terms of generating function. So for this we take solve first term, so that is a2 plus a3x plus a4x square. So what we need here to make this is gx. Actually in gx you see that we have a0, so x raised to the power 0. When we take a1, so x raised to the power n. When we take a2, so x raised to the power 2 with this. And here we have a2, a3x. So here what we need here, here we need to multiply, if we multiply here x square and here, so it become x cube, it become x4. So it means that we have to multiply by x square, and if we multiply by x square, so obviously we have to divide x square to maintain the equation, right? So now we multiply here x square and divide it by x square, so it becomes in terms of a2x2 plus a3x3 plus a4x4. Now to make the gx we need here a0 plus a1x terms, right? So we add these terms to make gx, and when we add this, so obviously we have to subtract is also minus a0 minus a1x to maintain the equation. So now we add this a0 plus a1x here and also subtract a0 plus a1x here. So now what is this up to here, a0 to this term are become the gx. So it is become gx, and this is minus a0 minus a1x upon x square. So like that all terms, all other terms you have to convert in terms of g. So these are the recurrence relation terms. So now when we convert into the g, so it become minus 3, and this is here what is have here, here we need a1x and here x square, here x cube. So we have to multiply x and divide it by x here, and then it become the gx if we add a0 here and subtract a0 here. So we add here, so it become gx minus a0 upon x, and this is already a gx, so this become 2gx is equal to 0. Now put here the initial conditions which is given in the question, a0 is equal to 2 and a1 equal to 3. When we put here, so it become this. So now we solve it and find the value of gx from here. So when we solve it, so we get the value of gx is 2 minus 3x upon 2x square minus 3x plus 1. So this is our the gx, right? So uh, if this is our the gx, our generating function, so now after this we use the partial fraction decomposition. You know that what is how to do the partial fraction decomposition. If you have any confusion, so you can see the uh, before lectures that in which that is a particular lecture for the partial fraction decomposition. So here we when we do the partial fraction of this term, so it become 1 upon 1 minus x plus 1 upon 1 minus 2x. So you have to do this yourself, because you know that how to do the partial fraction. In each and every question, when we using the generating function to solve the recurrence relation, we need the partial fraction. Okay, so it's necessary that you first understand how to do the partial fraction of any function. So now after that, this is our the partial fraction of the function. Now using the table, which table? Earlier I show you that the table, here we have this terms. So what is this is the generating function, or you can say that the reversely, if we have the generating function is this, so what will be the general term? That will be this one. So now here this is the generating function, right? So and to make the particular generative function, what is gx? Gx is our the summation n equal to 0 to infinity a n x raised to the power n. This is term of form of gx. So to become this form, what we can write here, this is 1 upon 1 minus x. So what is the generating, if our generating function 1 upon 1 minus x, it means that our gk term is 1. It means that with the summation it becomes summation n equal to 0 to infinity 1 raised to the power n x raised to the power n. In terms of generating function you can write this, because this is only gk. Now plus second term, we have 1 upon 1 minus 2x. So this is the generating function. So what is the generating function? If our generating function is 1 upon 1 minus 2x, so what is the term? Here you can see here, if we put here a is equal to 2, so it becomes this, means this is 2 raised to the power k. So our function is summation n equal to 0 to infinity 2 raised to the power n x raised to the power n. Clear? Now to reducing the expression here, means take out the summation, both sides cancel out the summation, so it become the terms only a n is equal to 1 plus 2 raised to the power n. So this is the, what is this? This is the solution of our the given recurrence relation. So like that you can find the solution of the given recurrence relation by using the generating function. Let's take another example. Here our recurrence relation is this: un is equal to un minus 1 plus 2 un minus 2, and initial conditions are given that u0 is equal to 3 and u1 is equal to 7. So same procedure we follow here. Multiply the equation with x raised to the power n and sum here we take 2 to infinity. Why we take here summation 2 to infinity? Because here our subscript are n, n minus 1, n minus 2. So lesser subscript is n minus 2. So to make it our initial condition is u0, right? So make it 0. We need that we put n is equal to 2. When we put is n equal to 2, so we get the our first initial condition u0. So we take the summation 2 to infinity. Clear? Okay, so now let's do the procedure here. Summation n is equal to 2 to infinity un x raised to the power n plus un minus 1 x raised to the power n to un minus 2 x raised to the power n. Now uh, one another way to do this is, here in this question you see that here we take that the exponent of x equal to the suffix of u inside the summation sign, means here when in the last example actually we do that, we have to make the generating function form, we divide or multiply by x or x square or x cube, like that. So here initially you can do this like that. Here if you, because in the generating function we have the same suffix, same same power of x, that is a suffix of u or a also, right? So here you have u and xn, it is same is here. Now you have to take the same power is here, means x raised to the power n minus 1 should be here if you have un minus 1, and xn minus 2 should be here if you have un minus 2. So we take the similar here, so it become, when we want to see that here x minus 1, it means that we have to multiply with x and divided by x, so it become x, and it become xn minus 1. So to come here n minus 2, so we have to multiply by x square and x raised to the power minus 2, so it become x raised to the power n minus 2. So directly from here you can do it. Now after when you expand it, so it become n is equal to 2 here, so u2 x2 plus u3 x3 plus u4 x4 and so on, and this is x, and this become, when you put n is equal to 2, so it become u1x u2 x2 u3 x3 and so on, and the last term 2x square, it become u0 plus u1x plus u2 x2 and so on. So now we know that our generating function gx, we can express it by u0 plus u1x plus u2 x2. So we solve first the first term of the recurrence relation, so that is u2 x2 u3 x3. So how can we solve it? You know that to solve it, only we need that we have to add u0 plus u1x here, and also we have to subtract u0 plus u1x. So now it becomes up to here, this term is become gx, and this is minus u0 minus u1x. Now this was our the recurrence relation. So all terms when we put in terms of gx, so it becomes, this is gx minus u naught minus u1x, and this is u1x u2x square. So what we need here to make the gx, we need that u naught, so you add here u naught and subtract here u naught, so it become gx minus u naught with x, and this is already a gx, so this is 2x square gx. Now solve it and put here the initial conditions in u naught and u1, that is 3 and 7. So when we solve it and find the gx here, so our gx is here become 3 plus 2 4x upon 1 minus x minus 2x square. What we do after here? After this we have to do the partial fraction of this, and what will be the partial fraction of this expression? So you know this. So when you do the partial fraction, first you have to factorize this quadratic equation and then do the partial fractions, because these are the linear functions, so it will, you have to take only the constant, so it become 10 upon 3 1 minus 2x minus 1 upon 3 1 plus x. So these are the partial fraction of this expression. So this was our partial fraction. Now we have to take using the table also here again. This was our table here. 10 upon 3, this is a constant, and 1 upon 1 minus 2x. So what will be the, if our generating function is 1 upon 1 minus 2x, so what will be the term here? Means in place of a you have 2, so it become 2 raised to the power k. And if we have 1 upon 1 plus x, so 1 plus x means our a is here minus 1, so it become minus 1 to the power k. So it is 10 upon 3 2 raised to the power n x raised to the power n in terms of gx when you write in terms of summation, and it is minus 1 raised to the power n, right? You can write it. Now reducing the expression here, only taking the terms, so it is un is equal to 10 upon 3 2 raised to the power n minus 1 upon 3 minus 1 raised to the power n. So this is our the solution of the given recurrence relation. Clear how to solve the recurrence relation by using the generating function? Okay, so let's take another example. Here we have the non-homogeneous equation, right? Because this is extra term here is 2 raised to the power n minus 1. So till now we solved the homogeneous recurrence relation. Now here we have the non-homogeneous recurrence relation. And initial condition is given that u0 is equal to 1. Here we need only one initial condition. Why? Because we have only the n and n minus 1. So we have the only linear uh, equation here. Now, same procedure we have to follow here. Multiply the equation with x raised to the power n, and here we take the summation 1 to infinity. Why we take here 1 to infinity? Because here our lesser subscript is n minus 1. So we take here summation 1 to infinity because our the initial condition is u0 is given. So to make the initial value 0, we have to put here n is equal to 1. So when we apply this becomes summation n un xn un minus 1 xn 2 raised to the power n minus 1 xn. Now same thing is here we have to do to make the generating function. We have to take the similar power and similar subscript of u. So to make the xn minus 1 we have to multiply here with x, and here to make the n minus 1 we have to also multiply with x here. So it becomes 6x, and this is x, this one. Now expand, when we expand it, so it become, when you put n equal to 1 here, u1x plus u2x2 plus u3x3 and so on, and here 6x, and this become u0 plus u1x plus u2x2 plus and so on, and this is x1 plus, when you put here n is equal to 1, so it become 2 raised to the power 0, x raised to the power 0, it become 1, plus next term is 2x 2 square x square plus 2 cube x cube, like that. Clear? Now we know that our generating function is u0 plus u1x plus u2x2. So when we solve the above recurrence relation, means if we use the first term, the first term is u1x, u2x2, u3x3. So to become the generating function, we have to add here u0. So obviously the subtract u0. So it becomes gx minus u0. Now this was our the expression. So now when we use all terms in terms of the generating function, so it becomes gx, this is our the gx minus u naught, and this is 6x, and this is already a gx plus. Now what is this? This is 1 plus, we write it 2 raised to the power k and x raised to the power k. So it means that this is 1 upon 1 minus 2k according to the table, right? So this series generating function is x upon 1 minus 2x. It's clear? Okay. So now put here the initial condition, that is given u0 is equal to 1. So this is our the expression here after putting the initial condition. Now calculate here the gx when we solve it. So our gx is become 1 minus x upon 1 minus 2x 1 minus 6x. So now we have to do the partial fraction of this. Already we have the factors here. So when we do the partial fraction, so it become, this is our the partial fraction of this, 5 upon 4 1 minus 6x minus 1 upon 4 1 minus 2x. Now we use the table here because these are the generating function and we need the solution. So to make the terms from the generating function, we need the table, and this was our table. So if we have the 1 minus 6x, so what will be the term here? It means a is equal to 6 here, so it becomes 6 raised to the power k. If we have 1 minus 2x, so it becomes 2 raised to the power k. So in terms of generating function, we can write it, our generating function is un x raised to the power n. 5 by 4 we can write it 6 raised to the power n, and this is, we can write 2 raised to the power n. So when we reducing it, so taking only the terms, that is un is equal to 5 by 4 6 raised to the power n minus 1 by 4 2 raised to the power n. So this will be the solution of our given recurrence relation. Easy? Yes, I think this is the so easy to solve the recurrence relation by using the generating function. Only one thing you have to remember, if you remember this table, so you can solve easily the generating recurrence relation by the generating function, mainly this term. Okay, so I hope all of you are understand how to solve the recurrence relations. So now this unit has completed today. So thank you. Today's lecture is completed now. Be happy, be healthy.